Although salt and sugar look very similar, they're both white crystalline substances, they behave very different chemically because they have different types of chemical bonds holding the atoms together. A chemical bond is the attraction two atoms or ions have for each other. There are three types of chemical bonds. Ionic bonds refer to the electrostatic attractions between anions and cations. Remember that metals on the left side of the periodic table tend to lose electrons to achieve an octet and therefore become more stable, and those form positive cations. And those nonmetals over on the right side of the table have a tendency to gain electrons when they ionize to achieve an octet, and they form negatively charged ions or anions. And when a metal loses an electron to a nonmetal, forming a positively charged ion here and a negatively charged ion there, the attraction between those two ions is an ionic bond. And sodium, with its one valence electron, then will donate it to chlorine to become more stable, and that gives chlorine an octet. It'll also give sodium an octet. Sodium, having lost an electron, then gets a positive charge. Chlorine, gaining an electron, then gets a negative charge. And there's the positive-negative electrostatic attraction that makes that an ionic bond. It's a very strong attraction. The second type of chemical bonds are covalent bonds. And covalent bonds result when valence electrons are shared between two atoms. Covalent. Sharing a valence. And we just looked at nonmetals gaining electrons to form ions so that they could bond with metals. But nonmetals also can bond with other nonmetals, and they do it covalently by sharing their valence electrons. Like these two hydrogen atoms. So here we have this hydrogen atom, and it has one valence electron, and then we have this hydrogen atom, and it has one valence electron, and they both have a 1s orbital, which they would like to have full with two electrons in it. And so they come together and let those shells, orbitals overlap, and share the two electrons, and now each of them has a pair of electrons. And the third type of chemical bond is the metallic bond. Metallic bonds are found in metals like copper and aluminum, and they're the reason why these metals are such good conductors of heat and electricity. The electrons of any given atom in these types of metals don't belong to any one particular metal, but are kind of free-floating throughout here, which is why these types of metals are very bendable and good conductors of heat and electricity. And each of these types of bonds depends on the atom's electron configuration, and especially the atom's valence electrons, the electrons in the atom's outermost shell. One way of keeping track of valence electrons is to use Lewis symbols. A Lewis symbol is simply the symbol of the element with dots representing electrons. Here's sodium's electron configuration. Remember that sodium has one electron in its valence, in its third shell. And so we would write its Lewis symbol would be its symbol Na with one dot for that one valence electron. And here's chlorine's electron configuration. It has the core of neon and 3s2, 3p5 or 7 valence electrons in its third shell. And so when we write chlorine's Lewis symbol, we would write the symbol for chlorine and then add 7 dots. 1, 2, 3, 4. Remember, share before you pair, Hund's rule. 6, 7. Now remember the octet rule. Atoms are going to gain, lose, or share electrons until they're surrounded by an octet, or 8 valence electrons. And here, chlorine just needs one more to complete its valence. And here, sodium has 1 in its valence, which if it gets rid of that 1 valence electron, that means that now sodium will also have, a valence of 8 in its second shell. And so sodium. with its really low ionization energy, is very easily going to give up this valence electron, and chlorine, with its very high electronegativity, is going to pull that electron toward it. And so what we end up with is sodium, having lost an electron, getting a positive charge. It now has one more proton in its nucleus than it has electrons. And chlorine, having gained an electron, now having one more electron than it does protons, now has a negative charge. And that positive negative attraction, that electrostatic attraction, forms the ionic bond between sodium and chloride, forming a really stable salt, sodium chloride. Now remember that sodium is a really reactive metal and chlorine is a really reactive nonmetal. And so both of these elements, or atoms of these elements, contain a large amount of potential energy. And so when this exchange of electrons does take place, that energy is given off. This is a really exothermic process. And because this is such a reactive metal and this is such a reactive nonmetal, and so much energy is given off as a result of this new bond forming, sodium chloride then ends up being a very stable compound. And we can give a value to just how stable that new salt compound that was formed is. And we call that lattice energy. Or how much energy is it going to take for me to take my nice stable sodium chloride ionic compound and break it apart and separate it back into its sodium and chloride ions. And that would be for 1 mole of the compound. And if we take our nice stable sodium chloride salt and blast it back into sodium ions and chloride ions, the amount of energy that it's going to take is going to be 788 kilojoules per mole of salt. So it's a very endothermic process. It's going to require a lot of energy to break that attraction. And of course, as we said before, then if we reversed that process, looking at the formation of sodium chloride, then it's a very exothermic process. Formation of ionic compounds is always going to be an exothermic process. So the delta H formation of an ionic compound is always going to be a negative value. And the attraction between those ions and those compounds is really strong, which is the reason why most salts are hard and brittle and have really high melting points. Remember, Coulomb's law says that potential energy is going to be proportional to the charge of the ions over the distance between them. And so lattice energy is going to increase as the charges on the ions increase and their radii decrease. That's going to form the most stable compounds. While we're talking about how metals form ionic compounds, it's important to discuss what's going on with the transition metals because they behave a little bit differently. Many of them can form more than one type of ion. Copper, for example, can be copper plus 1 or copper plus 2. And iron can be iron 2 or iron plus 3. And these transition metals have d orbitals that come into play here. Here's copper's electron configuration. If we think about where those electrons actually reside, by putting this into a box diagram, this is what it would look like. And so the important thing to remember when you're dealing with these transition metals that have these d orbitals is even though when filling, electrons would go into the 4s orbital first and then into the 3d orbitals, the last ones in aren't necessarily going to be the first ones out. What copper actually will end up doing is losing its 1 electron from the 4s orbital and then promote that electron into this d orbital right here. And so what copper ends up with then, in this instance, would be copper copper with a +1 charge, which is really nice and stable because it's got this full D subshell. And one last thing to consider while we're on the subject of ionic bonding is the polyatomic ion. This is the ammonium polyatomic ion, NH4+. Structurally, it looks like this. We've got nitrogens covalently bonded to hydrogens. What it actually is an ammonia NH3 molecule with an additional hydrogen or an additional proton bonded to its unshared pair. And so that proton gives this molecule a positive charge. And so a polyatomic ion then is a group of covalently bonded atoms that carry a net overall charge. And it's important to remember that when dealing with ionic bonds, that the polyatomic ion is going to stay together as a species when it bonds with other ions. Here's a sulfate ion, SO4 -2. So we have 4 oxygens bonded to 1 sulfur, and it's got actually 2 additional electrons here, which give it a -2 charge overall. So it's covalently bonding these sulfurs to the oxygen, but because there's 2 extra electrons, there's a -2 charge on the entire compound. And so again, polyatomic ions are going to stay together as a species when they bond with other ions. Now, most of the compounds on the planet are not ionic compounds or salts. Remember that salts are crystalline solids and high melting points. But solids with low melting points, think paraffin, wax, and gases, and liquids, belong to a different group of compounds called molecular substances. The molecular substances share their valence electrons in a covalent bond. Consider hydrogen, our diatomic molecule. We have 2 atoms of hydrogen with equal electron affinities. They're both hydrogen. Each one has 1 valence electron in its 1s orbital, and these 2 orbitals will overlap. And now they share a pair of electrons. And so each then in their 1s orbital has a pair of 2 electrons available. And that makes for a pretty nice stable s orbital. So these shared electrons then form a covalent bond. And since there's an equal amount of repulsions and attractions between the electrons and the protons in the nuclei, and repulsions between the 2 nuclei, since these are both the same element, hydrogen, then each of these hydrogen atoms is pulling on these, or attracting these electrons to themselves equally. And so since these electrons are being shared equally between these 2 hydrogen atoms, then this is considered to be a non-polar covalent bond. We would write the Lewis symbol for hydrogen like so. And if we add a second hydrogen, now we're creating a Lewis structure. And the Lewis structure is going to show those bonding electrons as a line. So one line then represents a pair of electrons shared in a covalent bond. A Lewis structure would also show unshared pairs of electrons, as in this chlorine atom. 1 chlorine atom with 7 valence electrons, and a second chlorine atom with 7 valence electrons. And looking at each of these chlorine atoms as orbital box diagrams, you can see here's the orbital where we have room for 1 more electron. Here's the orbital where we have room for 1 more electron. And so what happens is those 2 orbitals then will overlap like that, and they're each of these will be a shared pair between those 2 chlorine atoms. And so the Lewis structure for a chlorine molecule then would look like this, with a line representing the shared pair of electrons, along with all of those unshared electrons as well. So when one pair of electrons is shared in a molecule, that's known as a single covalent bond, as with our hydrogen molecule. You can also have a double covalent bond, in which case you would have two pairs of electrons being shared, as we have with the oxygen molecule. And in a triple covalent bond, three pairs of electrons are shared, as in nitrogen. Let's also take a moment to take a look at bond length. Bond length is going to be the distance between the nuclei involved in a bond. And so a single bond, sharing of a single pair of electrons, is going to be the longest. And as you increase the amount of electrons being shared in a bond, then the bond gets smaller. And so a double bond then is going to be a little bit shorter than a single bond will, and the triple bond would be the shortest of the three. Now we need to look a little bit more closely at these covalent bonds. We have here two examples of covalent molecules. This one is oxygen, and this one is nitrogen. And so we have two oxygen atoms covalently bonded together. And since they're both the same element, they both have the same electronegativity. They both have the same greediness for the electrons that they share. And so they share that pair of electrons equally. Same thing here with nitrogen. Two nitrogen atoms both have the same electronegativity. Both are going to pull on these shared electrons equally. So when electrons are shared equally by the atoms in the bond, we say that that is a non-polar covalent bond. But what happens when we have two different elements, in this case chlorine, bonding to hydrogen? The electronegativity values of the atoms involved are important. And so here's a table of electronegativity values. And chlorine is weighing in at 3.0, where hydrogen is 2.1. So there's a pretty decent difference between hydrogen and chlorine. Chlorine is a lot more electronegative than hydrogen is. And so chlorine then is really hanging on to the shared electron that it's sharing with the two electrons that it's sharing with this hydrogen. And so since chlorine has a greater attraction for that shared pair of electrons, then it forms a dipole. Since that shared pair of electrons is attracted more to the chlorine atom than it is to the hydrogen atom, and then we have a polar covalent bond, meaning the electrons are being shared unequally. And that leaves us with a molecule that has a partial negative charge on the chlorine end and a partial positive charge on the hydrogen end. So even though we looked at the actual values of electronegativities when we were taking a look at that polar covalent bond, you should know that those values aren't really going to be available to you when you're making these determinations. So it's important to remember the trend for electronegativity being greatest up here with fluorine and actually the noble gases, and decreasing as you go down and to the left. And so you're always going to have a big difference in electronegativity between metals and nonmetals. And you're going to have a smaller difference in electronegativity in elements that are going to be closer to each other on the periodic table. And this is really important to remember if you're not able to take a look at the electronegativity values, because those differences are what tell us whether we're going to have an ionic bond or a covalent bond, polar or a nonpolar covalent bond. And it works something like this. If the difference in electronegativity is between 0 and 0.4, say you have two elements that are the same, two hydrogens or two oxygens, that would be a difference of 0. Or you could have a carbon and hydrogen bond, hydrogen being 2.1 and carbon being 2.5. That's a difference of 0.4. So carbon and hydrogen then would be a nonpolar covalent bond, just like two hydrogens would be a nonpolar covalent bond. If the difference in electronegativities is in the range of around 0.4 to around 1.7, then that bond is going to be considered polar covalent. So hydrogen then, with a rating of 2.1 versus chlorine with a rating of 3.0 gives us a difference of 0.9. And so the bond between a chlorine and a hydrogen then would be polar covalent. And if the difference in electronegativities between the two elements involved is equal to or greater than around 1.7, then we're talking about an ionic bond. And since we know ionic bonds typically happen between metals and nonmetals, we'll take a look at sodium with a value of 0.9 and chlorine with a value of 3.0 gives us a difference of 2.1, which is clearly in the ionic range. And you should also keep in mind that these are not exactly dividing places here. That this is when you're at a difference of around 0.4, you're somewhere between being nonpolar and being polar. You're right in this gray area, just as there's a gray area in between really, really, really polar and ionic. And so these are just kind of guidelines for you to think about. But mostly we know that when we're taking a look at elements that are metals bonding with nonmetals, opposite sides of the table, we're talking about ionic compounds. Polar covalent compounds are pretty much going to be anytime we have a metal and a nonmetal that are two nonmetals that are different from each other. With the exception of hydrogen and carbon, which form a nonpolar covalent bond. And then for the nonpolar covalent bonds, carbon and hydrogen being two different elements that form nonpolar covalent bonds, and then anything that is two elements bonded together that are the same, like O2 or H2 or N2, all would be nonpolar covalent. And really, those are the best guidelines that you could use overall. And so, since ionic species are very different from molecular species, we have different rules for naming them. As you recall, when we're talking about an ionic species, metal and a nonmetal, we name the ions sodium chloride. And in the case of transition metals, we include the charge, copper 2 sulfate. And with molecular species, we use prefixes di, tri, and tetra, and so forth. I hope this has been helpful.